Okay, class, this is Coach Williams once again. We are going to wrap up with this third video. I do believe we may have one additional short video for 4.7, but as far as our quizzes go, this is the last quiz that we will review. This is for Unit 4 test, which will be on Thursday. This is homework, check, or quiz over sections 4.5 and 4.6. The scatter plot shows students' scores for quiz 1 and quiz 2, and the first two things it's asking us to do here is to find out, number 1 or 1A, what is the quiz 1 score for the student who earned a score of 13 on quiz 2. So we're going to have to be able to read this graph here and notice that they don't necessarily look the same. As far as where the plots go. This one goes a little further down, this one goes up over here. We've got points here on quiz 1 score. We're trying to find the score here for the one that scored a 13 here. Well, 13 is going to lie right in the middle between here, because if you notice these go by 2, so 2, 4, 6, 8, 10, 12. This would be 14, so between 14 and 12 you'd have 13. So if we follow that across the graph, then this would be the score, and if we follow that down to the quiz 1 side, we're going to notice that that lies between 18 and 20. So the student who scored a 13 on quiz 2 scored a 19 on quiz 1. Alright, did any students earn the same score on both quiz 1 and quiz 2, and explain? So what we're looking for is a point that matches up on this side where it matches up here. If you look here, this is a 12 for quiz 2, this is a 10 for quiz 1, so that doesn't work. The next point over, we have what looks like a 15 for quiz 1, and if you go down here, we have a 15 for quiz 2. So yes, we have student scored 15 on both quiz 1 and quiz 2. Looking at the rest of them, this is still a 15. That won't be the same. This is a 14 and that is an 18, so none of these other points actually match up. This one here is at that would be an 18, so that would be 19, and 19 is sitting on 20. This one's at 18 and 20. None of these other ones will actually have the same score on both sides, other than the one student who scored 15 on both quiz 1 and quiz 2. Okay, number 2, 3, and 4. They're asking us to tell whether X and Y show a positive or negative or no correlation on the scatter plots that are given here. And if you'll notice here, we talked about this in class, if we can lay our pen over most of the points, most of the data points, and it covers most of those data points, then we pretty much have a correlation. Now in this case, from left to right, this pen points in the negative direction or the downward position. So this is a correlation. It is also a negative correlation. On number 3, if you'll notice, I can't really cover up the majority of the points by going anywhere on this graph. It just doesn't work. The scatter plot of data points here is just too scattered, to make a pun there. The scatter plot's too scattered, so this one is going to be no correlation. I'm going to abbreviate correlation just for sake of time here. On number 4, once again, I can take this pen and I can lay it over most of the data points here and cover them up. And if you'll notice, this is going in a positive direction from left to right. We always read slope information from left to right here. So this is going in a positive direction from left to right. So this is going to have a positive correlation. It does have a correlation because the points can be closely related to a line, and it's a positive correlation. Okay, on to the back. Here we're going to use this table that shows the number Y of pineapple plants in a garden X years since 2004. Write an equation that models the approximate number of pineapple plants as a function of the number of years since 2004. Now, we have demonstrated this, and I'll have to probably do a little add-on to this video with a graphing calculator. But we have demonstrated with this that you can actually do this in the calculator by going to Stat and editing your values, putting in your X values into list 1, your Y values into list 2. And I noticed that several students did this on their quizzes. And that's fine, that's okay. What you're going to come up with, though, is a value of like, for your slope, you're going to come up with like 2.02 or 2 point something, some decimal place there. And so you're going to have to realize that you can't increase by partial or parts of a plant, or decrease by parts of a plant. So it's going to have to round to whole plant values. When we do that, you're going to see that this equation was going to be 2x because we were 2 point something, and that was putting this into the stat and then calculating the linear regression. And then we also noticed that there was like a 0.5 something decimal value for the B or the y-intercept, and obviously you can't start with half a plant, so you'd have to round that up to a 1. So if you use the calculator to solve this, you'd end up with y equals 2x plus 1, rounding to whole plant values. And that's sufficient. That does give us the equation that models the approximate number of pineapple plants as a function of the number of years since 2004. That's one way to do this problem. And if we interpreted the slope and the y-intercept of the line of fit here, we started with one plant, is what the plus 1 tells us. That's what the y-intercept tells us. That means we started with one plant. And then the slope tells us that we are adding 2 plants every year. Now, if you didn't want to use the calculator in this case, you could take some data points. These are just data points, obviously. They're not an exact line, but if you take some data points, you can kind of grasp or get the slope from those data points. If you took a couple of points, let's say we took 8 and 16, and we took 3 and 7. And you subtracted your y values from each other, so we're going to find the slope. We're going to say 16 minus 7 over 8 minus 3. Okay, we're going to find out that this is going to be, what, 9 over 5. And 9 over 5 is roughly 2. It's pretty close to 2. So we'll say approximately 2. If we took a couple of other ones just to try to see if they were anywhere closer, we could say 9, let's use 9 and 19, and 3 and 7, so 9 minus 3 over 19 minus 7, and that would give us, I'm sorry, I did that upside down. Let's scratch that. 19 minus 7 over 9 minus 3. Let's flip that over. That should be our change in y over the change in x. All right, so 19 minus 7 over 9 minus 3. That would give us 12 over 6, and that does give us exactly 2. And so you're going to see that our slope is about 2. So you could do it by choosing a few random points and finding your slope. And then if you know that your value is 2 here, you could graph this on a little graph and kind of see where your y-intercept would be. It's going to be something around 1, maybe a little less than 1, but you can't start again with a partial plant, so you have to start with at least a whole plant. In this case, it'd be 1. Okay, let's look at number 6. And on number 6, they're wanting us to use residuals. And the residuals here means that we're going to extend our graph, our table here, and this we demonstrated in class and also in our notes. And when we're using residuals, what's given to us in the table is the actual data points. What they also have given us is a model that we believe could be a good fit for the data in the table. The model is a line. This is our model. Okay? And so if we plug in the x value into this equation, then it spits out a y value that's on the line. And what we're going to use residuals for, residuals tell us how far away the actual data point is from the model value that comes out on the line. So we can tell if the data points are pretty evenly dispersed, then the line must be going through the middle of these data points. And pretty much, hopefully we're looking for something that's pretty close to the data points. The line's going to be evenly dispersed in the middle of these data points. So this is going to be my model y value. This will be my residual. Residual just meaning the distance between the two values. If I plug in a -4 into here, that's going to be a -28 divided by 2, which is 14, minus 8, which is going to be a -14, -8 is going to be a -22. Okay, so -4 times 7, -28 divided by 2 is 14. So a -14 minus 8 is a -22. So if I plug this in, then I'm going to get a -22 out of it. So the line, I like to do this as well. This is my line. -21 is above that line by one value. And because it's above it, it's positive. Okay, doing the next one, -3. It's going to be a -21. -21 over 2. Minus 8 is going to give me a -18.5. This one is going to be 0.5 below the line. -2 is going to be a -14. -14 divided by 2 is going to be -7. -7 and -8 make a -15. This one happens to be right on the line, so the residual is 0. 1 times 7 is -7. -7 divided by 2 is a -3.5. -3.5 and 11 is going to be an 8. I'm sorry, it's going to be a -11.5. So this one's going to be off by 0.5, and again, this is below the line, so that's a -1/2. 0. Well, 0 times that's just 0, so it just leaves us with a -8. So the residual between these two is just 0. 1 is 7 over 2, which is 3/2, or 3.5, I'm sorry, 3.5. And 3.5 minus 8 is going to be a -4.5. So this is also going to be a 0.5 away. This is going to be a little higher than the line, so this is going to be a positive. This data point's above the line. Put in a 2. 2 times 7 is going to be 14. 14 divided by 2 is 7. Once again, the 2's would just cancel. So 7 minus 8 is going to be a -1. That is right on the line. And you can see that as these data points are going along here, the residuals are very close to the line and they're evenly dispersed. They're either right on it or they're -5 above, -5 below. We've got 1 above. Here, if I did 3 times 7 is going to be 21 divided by 2 is going to be 10.5 minus 8 is going to be 1.5. This is above the line, so this is a positive 0.5, and 4 would be 28 divided by 2 is 14 minus 8 is going to be 6, and that's going to be right on it. Now, the points are evenly dispersed. The points are evenly dispersed. If you notice, the line goes along here, touching some of the points and just barely above or below the rest of them. So this is points are evenly dispersed. Y equals 7 over 2x minus 8 is a good fit. Okay, number 7. Number 7 is going to be where we need to use the graphing calculator, and what I may do is just add an addendum to this video here, a quick link here to show how you can use the graphing calculator to put in these values into our stat button. If you go to the stat button on your calculator, you'll be given an option to edit list 1 and list 2 values. List 1 will be your x values, so this will be your list 1, and then list 2 will be your y values. You'll put those into the list. Then once you get those in, you will hit stat again. You'll arrow over to calculate, and then you'll go down to linear regression. This is all in class. We've done this. We've explained this in class. Most people should know how to do it. Like I said, I will add a video explaining how to do that with a calculator so that you can see that actually being done, the process being done. If you put these values into the calculator, you're going to come up with something like this. It's going to have a readout where y is going to equal ax plus b. Okay, y equals ax plus b, and then it gives you the value for a, it gives you the value for b, it gives you an R2 value, and it gives you an R value. This is our correlation coefficient. Okay, that is our correlation coefficient, the R value at the very bottom. The A value that it's going to give you is what you plug into into this equation. The B value is going to be what you plug into the B value in, or the position in this equation. This particular one, I believe, comes out to be like a negative 1.125 or something like that. We'll confirm that here in a minute. And the B value is going to be like a 32.7 or something along those lines. The R value is a negative 0.997, I believe, or something roughly that area. So if I'm writing the equation of the line of best fit, which is what the calculator does, it gives us the line of best fit. It's going to be y is equal to negative 1.125. I'm not sure exactly what it is. I'm just going to give it a good guess here. We'll correct this in a few minutes. Then we're going to add to that the b, which is 32.7, and this is obviously times x. The first one's times x. That's the equation. Now, we know that if our R values, let's go over here and we'll write this little chart down. If R equals a negative 1, it's a strong negative correlation. If R equals a positive 1, it's a strong positive correlation. And if R is close to or equaling 0, it is no correlation. So, it's strong correlation if it's negative 1 or positive 1. We just have to decipher which one it is. If it's closer to 0, it's no correlation. This one is very close to a negative 1. So, being that this is close to negative 1, then the interpretation of the correlation coefficient is that this has a strong negative correlation. So this is our line of best fit for the data, and we know by the correlation coefficient that this has a strong negative correlation. And that concludes the video for 4546. We will follow up with a video on the calculator work for this as well.